What happens to the light rays after passing through a convex lens? It converges the light rays at the focus of the lens. Let us study the image formed by the convex lens for various positions of the object. To study the nature of images formed due to a convex lens. In order to study the images formed by a convex lens, we will use, for the sake of simplicity, a linear object like a candle kept perpendicular to the principal axis of the lens. A ray emitted from the top S of the candle travels parallel to the principal axis and reaches the lens at point P, from where it deviates to pass through the focal point F2 of the lens. Another ray from the top of the candle passes through the optical center O of the lens and travels straight to intersect the previous ray at point S'. An image is formed at this point where the two rays coming from the object intersect each other. Thus, we have seen how an image is formed in a convex lens. But the image of an object changes depending on the object's distance from the lens. Firstly, when the object is positioned at an infinite distance, the rays coming from the object will be parallel to each other. These parallel incident rays can be of two types. 1. These rays can be parallel to the principal axis of the lens. And 2. They may not be parallel to the principal axis of the lens. In the first case, the parallel incident rays, after having passed through the lens, converge to intersect at the principal focus F2 on the other side of the lens. Due to this, a real, inverted and highly diminished image is formed at the focal point. While in the second case, the parallel incident rays from the object do not converge exactly at the focal point but at some point S' in the focal plane on the other side of the lens. And due to this, a real, inverted and diminished image is formed at the point S'. Secondly, if the object is positioned somewhere between infinity and twice the principal focus 2f1, then the incident rays from the top S of the object having passed through the lens converge at a point S' between f2 and 2f2 on the other side of the lens. Here, the image formed is real, inverted and diminished. Bringing the object closer and placing it on point 2f1 causes the image to move further, and it can now be seen at point 2f2. Here also, the image is real and inverted, but its size is the same as that of the object. On further moving the object closer to the lens so that it is positioned between 2f1 and f1, the image will be formed at a point farther than 2f2. Here, the image is once again real and inverted, but the image is enlarged. In other words, we get a magnified image when an object is placed between 2f1 and f1. If the object is positioned at the focal point f1, then the incident rays will produce the image at infinity. The image will be real, inverted and extremely large. And finally, if the object is placed in between the focal point f1 and the optical center O of the lens, the reflected rays seem to go away from each other, which means they do not intersect each other. But on producing them backwards, the rays meet at S' on the same side of the object. In this case, we get a virtual image of the object, which is erect and enlarged. Such certain image of the object cannot be obtained on the screen. Rather, it can be observed from the other side of the lens. To summarize, we have studied how an object kept at different positions with respect to a convex lens produces different types of images. Later on, we will study how this image formation can be applied for practical purposes in optical instruments.
హాయ్ ఫ్రెండ్స్, వెల్కమ్ టు హెచ్వర్స్ వరల్డ్ ఫ్రెండ్స్. మీరు అందరూ వీడియో చూస్తున్నారు ఫ్రెండ్స్. అలాగే సబ్స్క్రైబ్ కూడా చేసుకోండి ఫ్రెండ్స్. అలాగే షేర్ చేయండి ఫ్రెండ్స్. ప్లీజ్ ఫ్రెండ్స్, షేర్ చేసి లైక్ చేసి సబ్స్క్రైబ్ చేయండి ఫ్రెండ్స్. థ్యాంక్ యూ ఫ్రెండ్స్.